Welcome to the deep dive. Today we're sort of smashing together two really big ideas in chemistry: how fast things happen, that's chemical kinetics, and, well, where they eventually settle down, chemical equilibrium.
That's right. Two sides of the same chemical coin, in a way.
Yeah, exactly. And we're diving into the sources you've shared with us to try and connect these dots. Show how the speed of just one molecule bumping into another can scale up to affect industrial processes, or how that chemical balance determines, like, the pH of your coffee or even your blood.
It really is fundamental stuff.
So let's kick things off with speed. Think about mixing silver nitrate and sodium chloride solutions. You just drop one into the other and bam, you get this white cloud, silver chloride, forming almost instantly, like less than a second. Super fast.
Okay, hold that thought. Now picture, say, a pile of pure glucose sugar just sitting in the air. Now, theoretically, it should react with the oxygen, right?
Yeah.
To make CO2 and water.
Right, that's what happens in our bodies eventually.
Eventually, yes.
Yeah.
But just sitting there, you could watch that glucose for years, decades even, and you wouldn't see any measurable change. It just sits there.
Okay, so that gap instantaneous versus maybe never, that's huge. If all these molecules are constantly zipping around and colliding, why isn't every reaction just over in a flash?
And that's the million-dollar question, isn't it? That's what chemical kinetics is all about. Why do reactions proceed at the rates they do? We define the rate, scientifically as the change in concentration over time, maybe something like 0.0040 moles per liter per minute.
Okay.
But the reason for the different speeds isn't just about collisions happening. It's about the quality of those collisions.
Quality, okay, so not just bumping into each other. They need to be effective collisions? Is that the term?
That's it exactly, effective collisions. And for a collision to be effective, two key things basically have to happen. First, the molecules need to smash together with enough energy, enough force to actually break the existing chemical bonds. We call this the activation energy.
Energy hill. You mentioned that.
Yeah, think of it like pushing a boulder over a hill. You need a certain minimum push, that's L and AGDL, just to get it to the top. If your push is too weak, the boulder just rolls back down. The molecules just bounce off each other.
Okay, so enough energy. Got it. What's the second thing? It can't just be hitting hard, right?
Nope, it's also about hitting right. Orientation. The molecules have to collide in the correct alignment for the specific atoms involved in bond making and bond breaking to actually interact.
Like lining up properly.
Precisely. Take water reacting with HCl, hydrogen chloride. For that reaction to happen, the hydrogen end of the HCl molecule has to hit the oxygen atom of the water molecule.
Okay.
If the chlorine end of HCl hits the oxygen instead, it doesn't matter how much energy they have, they'll just bounce apart. Wrong orientation, no reaction.
So you need lots of molecules for frequent collisions, that's concentration, and if it's a solid, you want lots of surface area, like a powder instead of a chunk.
More chances for contact.
But temperature, that seems like the big lever you can pull. We always hear that rule of thumb. Reaction rate roughly doubles for every 10 degrees Celsius increase. Why is it so effective? It feels almost too simple.
Well, it's a bit deceptive. Yes, higher temperature means molecules move faster, so they collide more often. But honestly, that's the less important part of the effect.
Oh.
The really dramatic increase comes because raising the temperature significantly increases the fraction of molecules that actually possess enough energy to overcome that activation energy barrier, the ELAMA.
So it's not just more collisions, it's more successful collisions. Way more.
Exactly. You're not just making the cars drive faster on the highway, you're suddenly giving way more cars the turbocharged engine they need to get over the mountain pass. It's an exponential thing.
And that exponential relationship, that sensitivity to temperature, it's not just lab chemistry, it connects right back to our own bodies, doesn't it? Like with high fevers.
It's a very stark example, yeah. Our bodies are optimized to run all their essential chemical reactions at around 37 degrees Celsius, normal body temperature.
Everything's tuned for that.
Perfectly tuned.
Yeah.
But if your temperature climbs too high, say it stays up around 41.7 degrees Celsius, which is about 107 Fahrenheit, that's critically dangerous. Because all those finely tuned essential reactions start speeding up uncontrollably. They become chaotic. The body just can't regulate things properly when the underlying chemistry is going haywire like that. It's overwhelmed.
Wow. Okay, that's kinetics having life or death consequences. But let's circle back to that glucose example. The sugar just sitting there. It could react, thermodynamically speaking, but it doesn't, or at least not noticeably.
Right. The kinetics are incredibly slow due to a high activation energy.
So this suggests speed is only half the story, even if a reaction can happen where it actually stops or settles. That must be a whole different concept.
And that's exactly where we pivot. We
Yeah.
move from kinetics, how fast, to equilibrium, where does it end up? Many reactions are reversible. They can go both forwards and backwards. We show that with double arrows in equations. Eventually, these reversible reactions reach a state called dynamic equilibrium. Dynamic because reactions are still happening, both forward and reverse. But equilibrium because the rate of the forward reaction perfectly matches the rate of the reverse reaction.
So things are still moving, but there's no overall change.
Precisely. The concentrations of all the reactants and products log in. They become constant. Now, crucial point. Constant doesn't necessarily mean equal. You might have way more products than reactants or vice versa. They just stop changing.
And we have a way to quantify that endpoint, right? The equilibrium constant, K.
Yep, K is the number that tells us where that balance point lies. It's mathematically defined as the ratio of the concentrations of the products divided by the concentrations of the reactants, each raised to the power of their coefficient in the balanced equation.
Okay, so what does the value of K actually tell us?
It tells you about the extent of the reaction. If K is really, really large, say 10 to the power of 8, like for making ammonia, it means the reaction strongly favors the products. It goes almost to completion.
Lots of products, very few reactants left at equilibrium.
Exactly. But if K is tiny, like 10 to the minus 10 for dissolving, say, barium sulfate, that means the reaction hardly proceeds at all. It strongly favors the reactants. You put barium sulfate in water, and mostly it just sits there as solid barium sulfate.
Okay, hold on. This is where I think people, including me sometimes, get tangled up. You're saying the glucose reaction, which is incredibly slow, bad kinetics, might have a huge K, meaning it really wants to go to completion eventually.
It does. The overall energy change favors forming CO2 in water, so K is large.
But a reaction that's lightning fast, like the silver chloride precipitation, might have a relatively small K, meaning it doesn't actually go that far.
It could, yes. Or maybe its K is large too. The point is, and this is probably the single most important takeaway here, there is absolutely no relationship between the rate of a reaction, kinetics, how fast it gets there, and the value of K, equilibrium, where it ends up.
Okay, say that again. No relationship.
None whatsoever. K tells you the destination. Rate tells you how long the trip takes. You can have a reaction that desperately wants to get to products, large K, but faces a massive activation energy hill, so the journey takes forever, like glucose.
That distinction is critical. So once a system does reach that equilibrium balance, that standoff, can we mess with it? Can we push it around?
Oh, absolutely. And it fights back. This is where Le Chatelier's principle comes in. It basically states that if you take a system at equilibrium and apply a stress to it, the system will shift its equilibrium position in a way that relieves that stress.
It tries to undo what you did.
Pretty much. So if you add more of a reactant, the equilibrium shifts away from the reactant side, consuming some of the extra stuff you added and making more product.
Makes sense. What about temperature changes?
Temperature acts like adding or removing heat. Think of heat as a product in an exothermic reaction, one that releases heat, or as a reactant in an endothermic reaction, one that absorbs heat. So if you increase the temperature of an exothermic reaction, you're adding product, heat. The system relieves that stress by shifting left back towards the reactants, consuming heat in the process.
And we can actually see this happen sometimes.
Yeah, there's a classic demonstration. An equilibrium between colorless dinitrogen tetroxide, N2O4, and brown nitrogen dioxide, NO2. Going from N2O4 to 2NO2 is endothermic. It absorbs heat.
So heat is like a reactant. N2O4 plus heat equals 2NO2, brown.
Exactly. So if you take a tube of this gas mixture at equilibrium and heat it up, you're adding a reactant. Heat, the system shifts right to consume the heat, producing more brown NO2. The tube visibly gets darker brown.
And if you cool it down,
you're removing heat. The equilibrium shifts left to replace the heat, consuming the brown NO2, making more colorless N2O4. The tube gets lighter. It's the Chatelier in action, changing color right before your eyes.
That's cool. And seeing that visual response to stress, it feels like a good bridge to our next big topic, acids and bases. Because their strength is really all about equilibrium, isn't it?
Fundamentally, yes. How strong an acid is just comes down to how far its equilibrium lies to the product side when it reacts with water. Remember the basic definitions. Acids are proton donors. They generate hydronium ions, H3O plus Pia, in water.
And bases are proton acceptors, often generating hydroxide ions, OH.
Correct. Now, the key distinction we have to make here, similar to rate versus K, is between concentration and strength.
Right. People often use them interchangeably, but they're totally different.
Totally different. Concentration is just, how much acid or base you actually dissolved in a certain amount of water. Molarity, usually. Strength, on the other hand, refers to the degree to which it ionizes or reacts with water.
So like ADCl, hydrochloric acid, is a strong acid.
Right, because essentially 100% of the HCl molecules you put in water donate their proton to water. The equilibrium lies completely to the right, HCl plus H2O and H3O plus Cl.
But acetic acid, the stuff in vinegar, that's a weak acid.
Very weak, because its equilibrium heavily favors the reactant side. When you put acetic acid in water, only a tiny fraction of its molecules actually donate a proton, maybe like 4 out of every 1,000 molecules at typical concentrations. Most of it just stays as undissociated acetic acid molecules.
Okay, so how do we put a number on that weakness, that equilibrium position?
We use another equilibrium constant. Specifically for acids, it's called the acid ionization constant, Ka. It's set up just like any other K products over reactants.
And Ka values for weak acids are usually pretty small numbers, right? Because they don't ionize much.
Exactly. Often very small, like 10 to the minus 5 or 10 to the minus 10.
Yeah.
Dealing with those tiny numbers can be awkward, so chemists often use the pK scale instead.
The P function again, like pH.
Just like pH, pK is simply the negative logarithm, base 10, of the Ka. So Ka equals a negative log.
And because of that negative log, the relationship is inverse, isn't it?
Crucial point. A stronger weak acid will have a larger Ka value, closer to 1, meaning more products, but because of the negative sign in the log, it will have a smaller Ka in that value.
Okay, let me try an example. The sources mentioned formic acid, which is in ant stings, has a Cal of 1.8 by 10 to 4, and phenol, sort of an antiseptic, has a Cal of 1.3 by 1010.
Right.
So formic acid has the larger Cal, meaning it ionizes more. Therefore, it's a stronger acid, and it should have the smaller Cal.
You got it. Formic acid's pKa is about 3.75. Phenol's pKa is way up at about 9.89. Smaller pK, stronger acid.
Okay, that clicks. And these acid properties aren't just abstract numbers. They explain everyday things, too, like acids reacting with metals sometimes.
Yeah, whether an acid reacts with a specific metal depends on the metal's activity, basically, how easily it gives up electrons compared to hydrogen. Active metals like magnesium or zinc will react with acids like HCl to produce hydrogen gas.
But less active metals.
Like copper, silver, gold. They won't react with typical acids like HCl or sulfuric acid to produce H2. They sit below hydrogen in the activity series. Nitric acid is a bit different because it's also a strong oxidizing agent, but that's another story.
And the other big reaction is acids with carbonates and bicarbonates, right? That gives off gas.
Carbon dioxide gas, CO2, that's a really important one. It's the chemistry behind antacid tablets fizzing and, crucially, baking.
Baking powder. Right.
Yeah.
How does that work using this acid-base chemistry?
Well, baking powder is typically a mixture. It contains sodium bicarbonate, NaHCO3, which is our base, and it contains a weak solid acid, something like sodium dihydrogen phosphate, NaH2PO4.
So they're both solids just mixed together.
Yep. As long as they're dry, nothing really happens. But as soon as you add water, like when you make dough or batter, the acid and the bicarbonate dissolve and can react with each other. The weak acid donates a proton, the bicarbonate accepts it, and this ultimately breaks down to produce those bubbles of CO2 gas.
And the bubbles get trapped in the dough and make it rise.
That's the magic. It's a controlled acid-base reaction, timed to happen when you add liquid, all thanks to equilibrium principles.
Amazing. Okay, this brings us perfectly to our final and maybe most vital area. The chemistry of water itself, pH, and the body's own chemical defense system's buffers.
Right. Water is fascinating stuff. It's amphiprotic, meaning it can act as both an acid and a base. One water molecule can donate a proton to another water molecule.
It reacts with itself.
In a very, very tiny amount, yes. This is called the auto-ionization of water. Two H2O molecules can form an H3O plus ion and an OH ion. This happens even in absolutely pure water.
And this self-reaction also has an equilibrium constant.
It does. We call it $2, the ion product constant for water.
Right.
At 25 degrees Celsius, the Tylers is always equal to 1.0 by 1014. That value holds true for any aqueous solution, not just pure water. The product of the H3O plus concentration and the OH concentration always equals 1014.
Which means if you know one, you can find the other. If H3O plus goes up, OH must go down to keep the product constant.
Exactly. And because these concentrations are often incredibly small, like 10.7 or 10.11, we again use the P scale, pH.
pH is Dutch log H3O plus PC. The scale we all sort of know. Lower pH means more acidic, higher pH means more basic or alkaline.
That's the one. And remember, because it's a logarithmic scale, Each whole number change in pH represents a tenfold change in the actual H3O plus concentration.
So pH 6 is 10 times more acidic than pH 7. pH 5 is 100 times more acidic than pH 7.
Precisely. Pure water, where H3O plus equals OH, both are 1.0 by 10 to 7 m. The negative log of that is 7.0. That's our neutral point.
Okay. But our bodies and many chemical systems can't tolerate wild swings in pH. If you dump a bunch of strong acid or base in, things go wrong fast, so systems need protection. They need buffers.
Buffers, chemical shock absorbers for pH. A buffer solution is specifically designed to resist large changes in pH when small amounts of acid or base are added to it.
And how do they do that? What are they made of?
Typically, a buffer consists of a mixture of a weak acid, let's call it HA, and its conjugate base, A, or sometimes a weak base and its conjugate acid. The key is having both members of a conjugate pair present in significant amounts.
Okay, weak acid HA and its conjugate base A, like acetic acid and acetate ions.
Perfect example. So imagine you have this buffer solution. Now, what happens if you add some strong acid, which means you're adding H3O plus ions?
The buffer needs to neutralize it somehow.
Right. The conjugate base component of the buffer, the A, steps up and reacts with the added H3O plus A plus H3O plus base HA plus H2O. Basically gobbles up the strong acid and converts it into the harmless weak acid, HA.
So the H3O plus concentration doesn't shoot up?
It barely changes. Now, what if you add a strong base, meaning OH ions?
Then the other part of the buffer, the weak acid HA, must react.
Exactly. The HA donates its proton to the added OH HA plus OHA plus H2O. It neutralizes the strong base, converting it into water and the weak conjugate base, A.
So either way, the added strong acid or base gets converted into a weak component that's already part of the buffer system. The ratio of HA to A might shift a bit, but the overall pH jump is much, much smaller than it would be without the buffer.
That's the essence of buffer action. It absorbs the shock.
And the most critical example of this is right inside us. Our blood, its pH has to stay in an incredibly narrow range, right? Like 7.35 to 7.45.
Incredibly narrow, yes. If it deviates much outside that range, you get acidosis, too acidic, or alkalosis, too basic, and both can be fatal very quickly.
So how does blood maintain that stability? What's the buffer system?
The primary buffer system in blood is the bicarbonate buffer system. It involves carbonic acid, H2CO3, as the weak acid, and the bicarbonate ion, HCO3, as its conjugate base.
Carbonic acid and bicarbonate, okay?
Yeah.
Now wait, the pKa for carbonic acid is about 6.37. Doesn't that mean its best buffering capacity is around pH 6.4?
It does. A buffer works best when the pH is close to the pK of the weak acid, because that's when you have roughly equal amounts of the acid, HA, and base A forms.
But blood operates at pH 7.4. How does the body make a buffer centered at 6.4 work effectively way up at 7.4?
This is where the body gets clever and uses concentration ratios. Remember the Henderson-Hasselbalch equation?
Vaguely. pH equals pKa plus log of base over acid.
You got it. pH equals pKa plus log AHA, or in this case, Pa plus log HCO3 H2Cu3. This equation is key when the concentrations of the conjugate base and weak acid are not equal.
Okay.
The body deliberately controls the ratio of bicarbonate, the base form A, to carbonic acid, the acid form, HA, the blood. It maintains it at roughly a 10-to-1 ratio. Lots more bicarbonate than carbonic acid.
10 times more base than acid.
Right. So plug that into Henderson-Hasselbalch. pH equals 6.37, the pKa, plus log 101.
Log of 10 is 1.
So pH equals 6.37 plus 1 equals 7.37, which is right in the physiological range. By actively managing that ratio, primarily through controlling CO2 levels via breathing and bicarbonate levels via the kidneys, the body forces the buffer to operate effectively at pH 7.4, even though that's not its natural pKa sweet spot.
That is incredibly sophisticated. What a journey. We went from just thinking about how fast molecules collide, the sort of kinetic chaos, to finding this stable balance point in equilibrium, and then realizing that pH and our entire body's acid-base balance is just a direct consequence of controlling these equilibria.
It really ties it all together. And if you look again at that blood buffer system, managing it isn't just about staying alive day to day. It's also key to pushing physical limits. Remember, we talked about hyperventilation. Breathing really fast and deep.
Yeah, it forces CO2 out of the body.
Right. And CO2 is linked to carbonic acid, H2CO3, in the blood. So forcing CO2 out pulls that equilibrium, H2CO3 equals CO2 plus H2O, to the right. It reduces the H2CO3 level.
Okay, so less weak acid in the buffer pair.
Which, according to Henderson-Hasselbalch, if you decrease the HA term in the denominator, The log term becomes more positive, and the blood pH actually goes up slightly, a temporary mild alkalosis.
And this is the sprinter's trick you mentioned. Why on earth would an athlete deliberately make their blood slightly more alkaline before a race?
Because what's the main thing that limits performance in really intense short bursts of exercise like sprinting?
Lactic acid buildup makes your muscles burn.
Exactly. Lactic acid is, well, an acid. As it builds up rapidly during intense exercise, it releases protons, H+, and starts to overwhelm the blood buffer, driving the pH down. This acidosis impairs muscle function.
So if you start the race with your blood pH already artificially pushed slightly higher,
You basically give yourself a larger buffer capacity against the incoming lactic acid. Your body can absorb more of that acid load before the pH drops into the range where performance really tanks. It's like starting with a slightly bigger bucket to catch the acid rain.
so managing that delicate acid-base equilibrium down to manipulating the log of a concentration ratio can literally be the difference between winning and collapsing.
It can absolutely make that difference at elite levels. It's physiology meeting chemistry at the finish line.
So what does this all mean? It means the difference between flooring it and hitting a wall, chemically speaking, is governed by these intricate rules of speed and balance. The next time you feel out of breath, maybe just appreciate the incredible chemical balancing act your body is performing. Keep exploring the balance in the systems all around you.